Whether you know it or not, hips are used every day, and hip pain can be detrimental to our daily lives. Hip replacements are some of the most frequently performed surgeries worldwide. It's estimated that about 2.5 million people in the US are living with hip replacements. As baby boomers age and life expectancy grows, hip replacements are getting more and more common, with 850,000 patients expected to have hip replacements each year by the year 2030.
Here we have the hip joint. It's a synovial ball and socket joint wherein the ball, formed by the head of the femur, articulates within the socket, which is the acetabellum. Together, they create a freely moving synovial joint. The acetabellum is quite deep, and when compared to the glenoid cavity in the shoulder, it provides far more stability, but less flexibility as a consequence. If we now take a cross-section through the hip, we'll notice that the hip joint has a joint capsule, which is dense, irregular, collagenous connective tissue surrounding the joint. The joint capsule lays within the hip joint, lining the acetabellum. This is the labrum, made of fibrous cartilage, and the acetabellar labrum helps to increase the concavity of the socket and provide more stability for the joint. Also, surrounding the head of the femur, we see this articular cartilage, which helps to absorb shock and aid in the absorption of force. The joint cavity is filled with synovial fluid, and that lubricates and guides the hip joint, leading to a reduction in overall forces as well. Atop the femoral head, there is a round ligament that comes up from the head of the femur. It is called the ligamentum teres of the femur. It helps to give support to the hip joint, especially when it is flexed and laterally rotated. To help further give stability to the hip joint, surrounding the joint capsule, there are three additional ligaments. The first is the iliofemoral ligament, which courses from the ilium to the proximal femur. Next, the ischiofemoral ligament, which is more posteriorly located, goes from the ischium to the femur, and finally the pubofemoral ligament courses from the pubis to the femur, being more anterior located than the others. Together, these three ligaments help to stabilize the hip joint and limit hyperextension. During the surgical procedure for a hip replacement, the surgeon will cut each of these tendons and ligaments, making sure to limit the extent of his cutting to reduce healing time for the patient, and at the end, he will reattach each of these ligaments to the femur by drilling holes into the femur and suturing the ligaments back in place.
There are many different conditions and injuries that may cause a person to require a hip replacement. These include arthritis, hip fractures, tumors, and osteonecrosis, which is the death of bone tissue as a result of loss of blood supply to certain bones in the body. The most common failures of the natural hip joint stem from damage to the cartilage around the hip. Common signs a person may need a hip replacement include pain in the groin, swelling, loss of a range of motion, and stiffness of the hip. These symptoms can present themselves at any time, but are most common when doing motions such as walking, bending over, kneeling, walking up the stairs, and sitting down.
According to the Lane Regional Medical Center and the New York Hospital for Special Surgery, total hip replacements of the femoral head and the acetabulum are far more common than partial hip replacements of just the femoral head. In order to explain how these implants work, we have created a model that combines common materials and dimensions from published research data with common geometric features from implants made by Stryker and Johnson & Johnson.
The implant is composed of four parts: the femoral stem, the femoral head, the acetabulum, and the separating lining. The base of the implant is the femoral stem. The femoral stem is cemented roughly 12 centimeters deep into the femur and forms a 136.5-degree angle with the pelvis. It is constructed from cobalt, chromium, molybdenum alloy, an alloy chosen for its durability, corrosion resistance, and most importantly, lack of adverse reactions with body tissue. There are several other alloys that are used in hip implants, but almost all of them are constructed from either titanium or cobalt to achieve the same effect as before. The femoral head connects to the stem with no freedom of rotation, and in some designs is combined as a single part with the stem. The size of the head depends both on the size of the patient and the shape of the rest of the design, with recent implant designs shifting towards larger head sizes, but the median head size is around 36 millimeters. Ceramics are also often used for the femoral head and acetabulum because they are more durable and last longer than metal implants, but these implants are also significantly more expensive than metal, so most implants will use the same metal alloy as the stem for the femoral head. No matter what material is used, no implant can ever have two moving pieces of the same material in contact with each other because it creates extra friction that causes quick degradation of the implant parts. So, in order to combine a metal femoral head with a metal acetabulum socket, a lot of implant designs place a polyethylene plastic lining in between the femoral head and the acetabulum. Finally, the acetabulum, which is made from a similar cobalt or titanium alloy, connects the implant to the pelvis. In some cases, the acetabulum has pores that allow for the bone to grow into the implant, forming a natural connection between the implant and bone, but this leads to a long recovery time, so most acetabulum implants instead are cemented to the pelvis to decrease recovery time.
Our hip implant is created through two separate manufacturing processes. One using the cobalt chromium molybdenum alloy to create the femoral stem and acetabular cap, and the other using polyethylene plastic to create the acetabular lining. The process to create the femoral stem begins with the raw metal alloy ingot. This ingot is then heated until it is soft enough to be shaped. The metal ingot is then put into a forging press to first establish the 136.5 degree angle in the stem. It is then pressed into a die to establish the basic geometry of the femoral head. CNC milling and taper turning are used to refine the implant into the correct geometry. These steps are crucial in developing the curves and threading to attach the ball of the femoral head, as well as removing the excess material left over from the forge press step. These two steps are where the bulk of the material is removed from the metal implant. However, because the shape was cast, there's not as much metal that needs to be removed as when compared to if the entire part was made from milling. The next step is grinding, which further removes irregularities along the metal implant's surface. To create a finer finish on the part, sandblasting is used, followed by polishing. These two steps help to create a part that looks and feels complete. These final steps of milling, grinding, and polishing are essential to creating a functional hip replacement. The type of finish of the part is very important because it determines how the implant will react with the body. The ball for the hip implant is attached by screwing it onto the femoral stem to create the final model. The final step is a spray coat of titanium. This final coating will ensure that the part will seamlessly adhere to the implant area, and the recipient's immune system will not reject the part as a foreign body. The second part of the hip replacement is the acetabular cap. The manufacturing process for this part starts with a metal ingot, which is then heated and put into a forging press where the basic shape is created. Using CNC turning, irregularities are removed and more detail is added to the part. Drilling is then used to create screw holes in the part. Finally, the part is spray coated with titanium so that it will better adapt to the recipient's body. The final part is the polyethylene plastic liner between the femoral head and acetabular cap. This part is created through injection molding and then sanded down using machining. Along the manufacturing line for each of these three parts, there are rigorous inspections performed after each of the steps. These checks help to ensure each part is created properly and there are no defects in any of the final parts. Together, these parts form a hip replacement and they are ready to be implanted in a patient.
Hip replacements, just like any other part, will continue to be updated and their design will change as manufacturing processes evolve over time. Recent developments in hip replacement design mostly revolve around ceramic-on-ceramic parts. These parts have the advantage of being more scratch resistant and durable over time, which will decrease the chances of the part needing to be replaced as time goes on. Other possible further developments include research into changing the geometry of the hip replacement in order to decrease failure by dislocation of the joint. The loosening of the femoral head is the most common mode of failure for a total hip replacement. One recent development is increasing the size of the femoral head from 32 millimeters to 36 millimeters in attempts to decrease such failures. This change is just one example of the constantly evolving design process. The engineering design process is never finished. There is always possibility to improve based on customer feedback or advances in technology.